All right, the time is noon. So welcome everybody. We're excited to continue our new FAFP webinar series this afternoon and glad for the excellent turnout. So just some housekeeping things before we get started. Please make sure your video and audio are off throughout the duration of today's program. We'll ask Dr. Danyluk to answer questions from the audience at the end of her presentation. And we'll have a team of volunteers who will be monitoring the chat box and facilitating your questions with Michelle. So please do enter any questions you have directly into the chat box. We'll also be recording the program to post on FAFP.net, which has been recently revamped, so please check it out. Many of you know that we were supposed to have our annual educational conference in St. Augustine probably maybe a month ago, where we would have celebrated our 75th anniversary. We're lucky that many of the excellent presenters that we had lined up for our conference have agreed to present webinar series instead. Our speaker today is Michelle Danyluk. Dr. Danyluk is a professor and extension specialist of food safety and microbiology in the Department of Food Science and Human Nutrition at the University of Florida. She is situated at the Citrus Research and Education Center in Lake Alfred, Florida. Her current research and extension interests include microbial safety and quality, emphasizing the microbiology of fruit juices, fresh fruits, vegetables, and nuts. Michelle's extension program includes teaching programs related to FSMA, HACCP, GAPS, and other specialized food safety, security, and beverage processing programs to stakeholders. Michelle was elected member of the International Commission on Microbiological Specifications for Foods in 2016 and the IAFP Executive Board in 2019. Today, she'll be speaking about useful testing in food safety management. And with that, Michelle, I will hand it over to you.
Thanks, Jason. I'm talking muted, so that's gonna show how well this is gonna go today. Let me just share my screen and get my slides up. And we'll get going. All right, so I think everyone's seeing my slides now. I'd like to thank you all for joining me today at lunchtime to listen to me talking about what's going to amount to a whole lot of math. So hang up now, or put me on in the background if that's not what you signed up for. And I'd like to thank both the real Travis Chapin and all the real Travis Chapins on the call today for inviting me to give this talk. Like Jason mentioned, I am a member of the International Commission on Microbiological Specifications for Food, or ICMSF, and I'm going to talk today a bit about some of the work that organization has done on microbial sampling. So, microbial testing means a lot of different things to a lot of different people, and it's really important to understand what these different ways these different ways of thinking exist and sort of what they are, right? So some think that testing should provide a real wealth of data to analyze and determine the perfect sampling plan. Folks that love getting their hands on the data and the numbers. Others think that microbiological testing is a detective situation where the purpose of the information is to really identify an unknown or causative agent in an outbreak, for example, or in a situation where there's been a quality issue. Some think that testing provides an implied guarantee that a lot of a product is perfectly safe or absolutely unsafe, sort of a black-white line, without recognizing that there's a lot of uncertainty in results and that it's a lot of gray. And for others, microbiological testing is a practical quality control tool that provides information to indicate whether or not a process is performing as expected, and then use the information to identify trends that may call for improvement. For others, microbiological sampling might just be something that they've been told to do, right? A buyer or an auditor or someone said, I need you to test this sample for me and I need you to tell me the results. And they don't really think about it any more than that. And none of those reasons are wrong reasons for microbiological sampling. Certainly, microbiological sampling has a lot of different applications. We're going to talk about some of them today. We're going to talk about some of the underlying theories of why we might do microbiological sampling. And again, we're gonna hopefully have all of you go back and think about what your sampling program looks like and why you are or are not doing different things. Now, I'm not going to talk about all the different sampling that exist. I'm not going to talk at all about environmental monitoring as a sampling program because it's just not enough time in an hour. But you know, that's something that if you're interested in, I think there are subsequent speakers in this series that we'll be talking about. So Jason mentioned, and I mentioned, that I'm a member of the International Commission on the Microbiological Specifications for Food. We abbreviate that to ICMSF. The real Travis Chapin spent an awful long time at one point trying to provide a pronunciation to ICMSF that made a word like FSMA. He never was able to do it, and so the group has always just stayed with the acronym ICMSF. It's a group that's existed for a really long time. It has held annual meetings since 1962 when it was first formed, so it's over 50 years old. And currently there are 17 food microbiologist members from 14 different countries that sort of encompass a broad professional background. And for someone to become or to be elected a member of the International Commission on the Microbiological Specifications for Food, they're selected on their technical expertise and their background, not as national delegates. So there are not countries that have a guaranteed spot on the commission. Really, the commission is selected from delegates as our technical expertise of members. It also uses an extensive network of consultants and experts who are invited in for a meeting or two as necessary for voluntary work without honoraria. The recommendations of the commission have no official status at all, but the commission does partner with ILSI, FAO, WHO, and organizations like IAFP. I've listed the website there, icmsf.org. And I, at this point, want to take the opportunity to thank the many members and former members who over the years have helped to develop some of the slides that I'm using within this slide set. Interesting thing about ICMSF is that members have a mandatory retirement age of 65. So after the age of 65, you are no longer able to participate. So if you look at sort of what ICMSF has done and the history and the evolution of food safety management, you know, back again, the first meeting was in the early 60s, 1962. And in 1968, the first book on methods came out, followed by a second book about microbial sampling back in 1974. A third book that actually had 2 volumes, published in 1980 about ecology of microbiological food. That second book was revised in 1986, again talking about sampling plans. 1988, we have the ICMSF's take on HACCP that came out. Book 5 came out in 1996. I call it tables, but what it is probably the best definition of safe harbors and limits I've ever seen put together. And so it's really a large book of tables about limits for different microorganisms. Book 6 on microbiological ecology came out in the late 90s. And then in 2000, we sort of see a move away from testing more into a broader idea of risk management, sort of driven by some of the HACCP principles released earlier on. The second edition of book 6 came out in 2005. And in 2011, they released book 8, which is very much a book that takes the sampling plans discussed first in 1974 and then revised in 1986 and really modernizes them and is going to provide a lot of the foundational principles of the issues that I'm going to talk about today. Those are, yeah, they're talked about in book 7, but they're really, really defined and talked about in book 8. So book 8 is really broken into 2 different parts. The first part talks about principles of sampling plans, really. Utility of microtesting for safety and quality, how you use safety and quality for validation of control measures, for verification of process controls, for verification of environmental controls, and then how to use sampling for corrective action to reestablish controls, and then talk through microbial sampling in supplier-customer relations. And then the second part of the book, which I think is one of the most practical parts of really any textbook I've seen, goes through different product categories, and I've listed them there. And I think there's 18 different product categories that in total it really goes through and talks through what a sampling plan for lots might look like in each of those different categories. So I will talk through some of what has gone into that, but a lot more of the principles. So testing a food or food ingredients is based on testing against a number of different criterion for either pathogens or indicators, and it's a really common tool used to assess the effectiveness of risk management programs for food safety and quality. And really, despite wide use in the food industry and something that all of us talk about all the time, from a consumer level, and even to a certain extent within the food industry, there's a really limited understanding of what the underlying concepts that go into microbial food testing. And those are what I'm going to talk about in a fair amount of detail today. So when we talk about useful microbiological testing, you know, microbial sampling is very useful in many situations. And I identified some of them earlier when we talked through, you know, why different people think microbial testing is important. But it's important to identify contamination sources, you know, and you can think about that like as an example of E. coli, generic E. coli, as a useful indicator of water quality, either for potable water when we're talking about drinking water, or for agricultural water if we're talking about irrigating crops with agricultural water. Environmental monitoring, right, has the potential to identify a harbor site for pathogens that can facilitate proactive measures to address whatever the issue is in the environment. So there's a number of usefulnesses of measuring for pathogens in the environment. Utility or indicator organisms, so microorganisms that may be there to just indicate a total microbial quality or to indicate some sort of the presence of some sort of contamination, can evaluate the effectiveness of controls a lot through trend analysis is a really good way to do this. And we'll talk about trend analysis a little later. This may be useful not only to monitor process controls, but can also be used to indicate the potential for post-process contamination. And finally, you know, there's a really important purpose of microbial testing to identify when a problem occurs. And testing is a really, really important way to identify the root cause, which can allow for effective corrective action to be taken. So when we talk about microbiological testing, right, there's different types of microbiological testing. So it's really important to think about the need of why you're doing a testing. So there's the different types of tests are designed to give different data for different needs based on specific information. So it's almost like you should think of the whole concept of microbiological testing like a toolkit, and then select the correct tool to do the job. So what sort of a tool are we looking for? Are we looking at to look at the safety of the lot? Are we looking at it as a verification activity? Are we looking at it as a validation activity? Or are we investigating a loss of control around the products? Or are we looking at some sort of a surveillance of process control or distribution systems or ingredients or even end product use? So it's really important to really identify why you're doing the testing and pick the right tool for the type of job that you are doing. Now, when we start to talk about statistics and microbiological testing of food, we really need to remember that microbiological testing is inherently probabilistic in nature. And we're dealing with probabilistic events, especially when we're sampling for pathogens. And those pathogens are typically present in very low level in the food products. And what that means is a lot of the time when we do microbiological samplings, that because of the low level of microorganisms in that food product, it's not possible to find pathogens in the product being tested simply because we didn't find them. And because our microbiological testing to date is always a destructive product, so we take a sample and that sample doesn't stay in the food chain, it's destroyed during the sampling process. The only way we can ensure that a pathogen is not in a food is to test all the food, but that defeats the point because there's nothing then left to eat at the end. So testing, our only option here for testing is that we can only test a portion of the food. And if we're only testing a portion of the food, we can never prove the absence of something not being there. We can prove that it's there, but we can never test enough unless we test all the food to be able to test that something's not there. Now, with that being said, not finding the problem also tells us something important, and it's also, so those negative test results are also really important. They allow us to know that the pathogen we're testing for is below the limit of detection for the specific test we're using, and they provide a level of confidence that we know the number of pathogens is below the limit of the test. So we'll talk through those concepts coming up a little bit more. Now, as I previously mentioned, microbiological testing is essentially a series of statistical tools. And to correctly understand and interpret the results of a testing program, you really need to understand the statistical basics or basis of that testing program. So for example, microbiological testing relies on the assumption that contamination is randomly distributed and that samples are taken randomly and independently. And if that criteria or that assumption is not met, then you might need to come up with an alternative sampling scheme. And the reality is, when we think about randomly sampling food products, it's very, very hard to do. And when we're talking about a lot of food products, especially food products that are solid units, we don't necessarily know that they are contamination is uniformly distributed. So those are challenges we're facing already when we start a sampling program. So another concept that's critical to the idea of sampling is something called a defect rate. And so simply put, what a defect rate is the number of servings that contain one or more cells of the pathogen of what we are sampling for. So it's the number of servings in a batch of food that contain or a lot of food that contain the pathogen we're sampling for. And the more servings of food in a batch or a lot that are contaminated, the more likely it is that we'll find those contaminated servings when we do our sampling. Conversely, if the defection rate or the defect rate is low, and we all really want the defect rate in our food to be low, so for example, less than 2%, selecting a contaminated serving might be the limiting factor in your sampling plan for detecting a contaminated batch. So this idea of how frequently we find a pathogen in our product is called a defect rate, and that's a really important concept to understand in our sampling plans, especially as we drive that defect rate lower and lower through our process controls. It becomes more and more difficult to find a problem, and it sort of is a limitation of the tests that we're using. So here's where some of the math comes in. In general, when we talk about microbiological testing, we divide sampling plans into two general classes, and they're called variables and attribute testing. Now, variable testing uses the direct quantifiable data, and it really is seldom used in food testing. So we're going to talk primarily about attribute testing because it really is the main type of data or type of testing we do in the food industry. And what this type of testing does is it stratifies our results into two different categories or three different categories, either acceptable or unacceptable attributes. And so in what we call two-class testing systems, the attributes in some cases, in the first example of two-case sampling plans I've got up there, the attributes are defined into either presence or absence of finding the pathogen of concern. And this is what we commonly do when we're when we're testing for pathogenic bacteria, right? So for example, a sampling plan for Salmonella or Shiga toxigenic E. coli, like E. coli 0157H7, might be based on the simple absence of the organism, right? So two-class sampling can be a presence-absence where we just say, we've got no Salmonella in this many samples tested. So that's one type of two-class sampling. The other type of two-class sampling plans involves the use of quantifiable data. So this is where you're actually enumerating the number of pathogens, not just enriching for presence absence, but you're enumerating the number of cells, and you're stratifying the data into levels that are unacceptable or acceptable. And so the example I've got here is that we've set the limit at 100, and if the number is less than 100, then that's an acceptable sample. And if the number equals or is more than 100, that's an unacceptable data. So it's taking a number data and putting a line in the sand and saying, less than this is acceptable, more than this is unacceptable. And this sort of testing is often used for indicator microorganisms, things like generic E. coli or total coliforms, and can even be something like a total plate count. And if we look at our colleagues in other parts of the world, right, in Europe or in Australia, they even sometimes use this type of testing for Listeria monocytogenes, where they'll accept up to 100 CFU per gram LM in a food substance where it won't grow. So it's another common type of system. And then the third type of system is called a three-class sampling plan. And this is where the quantified data, so again, you're collecting counts in this case, is separated instead of a line in the sand where you say 100 is too much, but 99 is okay. In this case, you've got a line, and then you've got a marginal area in the middle where it's okay, and then you've got another line. And so you stratify in this case into three cases. One where things are acceptable, one where things are marginally acceptable, and one where things are not acceptable at all. And so the difference between the two-class and the three-class sampling plan is that in these three-class sampling plans, this is where we define this marginally acceptable approach, or marginally acceptable data approach. And so in the example I've got here, we've got less than 10 is acceptable, between 10 and 100 is unacceptable, and then between more than 100 would be unacceptable. So you've got that between 10 and 100, that's that marginally acceptable rate. And so in this approach, if all the testing data fall into acceptable range, then the food is acceptable. And at the other extreme, if all the food falls outside the acceptable range, at the higher end of the acceptable range, then the entire batch is considered unacceptable. And in between these two numbers is this marginally acceptable range, and we set a number or a percentage of samples that can fall within this marginally acceptable range and still consider it acceptable. So that is a lot of words that I use, and for those of you who are visible learners like me, these sampling plans might be better defined by these graphs right here. So what we've got in this case is a probability on the y-axis and a concentration on the x-axis, and we define these numbers. N is the number of samples we collect. M is that the lower limit, it's our acceptability number. M, so small m, is the microbiological limit for good quality. Big M or large M is the unacceptable level, and this area between big M and small m is that marginally acceptable amount, and we define C as the number of samples that can fall in that marginally acceptable amount for the sample to still be acceptable. So in our two-class sampling plans, which are here in the lower right, all we set is that low M, and it's sort of our shining line in the sand. And if you've got more than that small m in your sample, it's unsafe. And if you've got less than, it is safe, and it's that line in the sand. Whereas in our 3-class sampling plans up above, right, we've got that line in the sand that is this little m, and then we've got this area here in orange where it's marginally acceptable as long as it's below a certain number of samples or a certain percentage of samples that fall in that marginally acceptable range. And then at the end, we have the proportion that's actually defective. So we'll come back to these in a little bit, but these are sort of the different classes of the way we can sample for microorganisms. Now, one of the key attributes of all microbiological testing programs is establishing how stringent the program needs to be in terms of the likelihood of a target microorganism will be detected. And this can be, and usually is, a really complex decision since the degree of stringency is based on a ton of different factors. Unless it's not a difficult decision because somebody like a buyer who you're selling your product to or a regulatory authority has told you what those criteria will be. But included in those different parameters that you might have to discuss are: why are we doing the testing? What is the cost of the analysis? How often do we expect to hit the defect rate? What is the distribution of contamination in the sample? What is the number and size of the samples we need to collect? What is the frequency of sampling? What are the lower limits of the testing method? And finally, how much statistical confidence do we have in the testing method being required? So a bunch of different things go into this decision. Another key thing to think about is where we're going to collect the samples. And so within food production, the whole process of production, processing, distribution, marketing often involve really complex supply chains that can both involve, international sourcing and distribution of products. So the key question you might ask yourself is, in microbiological testing, where along the supply chain should we sample? And there are 2 key attributes that influence the type of samples to take and where and when to take them. So the first thing to consider is that contamination typically flows within the food manufacturing process, and that second, microbiological testing results at a specified point in the chain reflect the impact of all the manufacturing steps that happened above it. So if we sample an ingredient that's coming in that we're using within our testing process, results reflect the control of the supplier and changes that happened in the transport before that ingredient got to us. Whereas if we do an inline sampling during our manufacturing process, this really reflects the sum of all the factors that influence the product from the ingredient coming in through the product status up to the point in the processing where we took that sample. And then finally, if we sample at the end of processing and we do an end product sampling, the concept is exactly still the same. End product sampling is really the integrated sum of all the factors that impact microbiological status of the product from receipt of the ingredients all the way through to final packaging. Now, most manufacturers and most of us view end product sampling really differently. And this reflects, I think, more so than anything, a bias on our point, because this is where we lose control of the food, and the food generally comes under some sort of a regulatory control. So, end product testing really should be considered sort of the same as any other point along the way. Now, when we're talking about testing, most of us learn about analytical testing, if we learn at all, as part of some sort of a chemistry training where we talk about a lower limit of detection. So our test is good to test up to this amount of pesticide or up to this amount of chemical contaminant. And while the concepts are true in microbiological areas as well, where the increased signal can be achieved, but in the case of microbiology, we can increase the signal that we can detect based on selective media, enrichment, and genomic-based methods like PCR. So we can actually change the amount of signal we've got there. And I think it's important to remember too that in microbiological testing, It's a little bit different than chemical testing because we're not dealing with molecules, right? We're dealing with particles, and we're dealing with particles and bacteria that can grow. And this is important because at a very low level, we need to be concerned with whether the analytical unit being tested contains the microorganism we're actually looking for. And this gets back to that concept I talked about at the beginning, where we really have an assumption about uniform distributions for most microorganisms. And this idea becomes increasingly important as we move towards testing smaller and smaller sized analytical units. And as we move towards a lot of these omic-based technologies, we're testing a lot smaller analytical units than we used to test. And so we need to remember that sampling and making sure we collect a sample or collect a sample that has an organism in it, it becomes a really important part of this equation. So let's talk about this idea a little bit more. When we're dealing with the particulate nature of bacteria, the size of the analytical unit being tested really becomes the key determination for the sensitivity of the method. And that's not the way it works in chemical testing. So for every 100-fold decrease in the size of the test being sampled, there needs to be a corresponding 10-fold increase in the concentration of the target microorganism to achieve that high level of concentration. So in the example I've got shown up there, if you're testing 0.1 milliliters, which is this 100 microliters here at the bottom, you need about 200 cells per mil. Let's say you need about 200 cells per mil to be able to really find those cells. Whereas if we're testing only 1 microliter, what that means is that our concentration of cells in that sample needs to be 2-fold higher, or 10 or 100-fold higher. So it would be, or 100 times higher. So it would be 10 to the 4, or about 20,000 cells per mil, which is an awful lot of cells to be able to detect. And so we're in this situation where for a lot of microbiological testing, especially when we talk about looking for pathogens and things that we expect to be there at a really, really low concentration, we're in this situation of, you know, we simply missed finding the bacteria, and that's going to lead us to think that the bacteria is not there. And that's not the case at all. And there are ways, this is a huge issue, right? And there are ways for us to get around this issue and to get those mean log concentrations of the microorganism we're looking for higher, so that we have a higher degree of confidence that we're going to be able to detect them. And one of the ways we do that is to increase the analytical unit size. Say going from testing 1 gram of product up to 25 grams per product, or even up to 225 grams of product. By increasing the amount of sample we're collecting, we can increase the number, the likelihood of finding the organism we're looking for in that sample. Another option is to increase the number of units being examined. So instead of sampling, say, 10 units, we sample 100 units. And so by increasing the number of samples we take, we can again increase the probability that we're gonna find a problem. And there's another way we can do it in microbiology, and this is taking advantage of the fact that sometimes we can concentrate samples and sometimes we can enrich a sample. Oh, I moved on a slide and I didn't mean to do that. Sorry, guys. So concentration is a technique we can use, which is common for water or other liquids, and that's where we pass a relatively large volume of liquid through a filter. That filter then captures the bacteria and lets the liquid flow through. And in some instances, we can filter even up to 100 liters of a sample. And then that filter can then be transferred onto microbiological plates or go into some sort of a media that allows a colony to develop, and we can get a count that way. For enrichment of samples, this is where we really take advantage of the fact that bacteria can grow. And in different types of liquid media, So we transfer the units into that broth liquid media, allow the bacteria to grow under standardized conditions, making sure that our enrichment conditions are targeted for whatever type of bacteria we're testing for. And the way you sort of need to think about this is that you've got one cell per whatever analytical unit of sample you've got. And if you're going to do some sort of a rapid test and you're going to use 10 or even 1 microliter of that enrichment sample, you need to make sure that that broth can grow the sample to the concentration you need. So again, in the example I used before, you need to turn that one cell, let's say per a 25-gram sample, into 20,000 cells if we're only going to take 1 microliter of it. And that's 20,000 cells per mil. So that's the tremendous amount of growth that has to be able to happen in these enrichment broths. Now, the problem with enrichment is that it's really hard to get that quantitative data, those counts of microorganisms, if you're using a 3-class test or a 2-class test that doesn't, or a 2-class plan that doesn't rely on presence-absence data. So sampling is really important, enrichment is a really great tool when you're looking at presence-absence. Okay, so to look at this another way, to talk about one of the things I said you could do is to increase the number of analytical units. And that's what this slide shows. So what we've got on the y-axis, or sorry, the x-axis, the bottom axis here is the percent defective. So how often do you find a defective sample in your sampling lot? And so we've got 0, 5, 10, 15, and 20. Again, hoping that you'll never have more than 20% of the food you're producing over whatever micro criteria you set. And then the probability of acceptance based on the number of tests you take is here on the y-axis, going up to 100. So looking at 3 different number of samples collected, the purple line assumes you collect 15 samples, the blue line assumes you collect 30 samples, and the green line assumes that you collect 60 samples. And we've decided here that our criteria is no detection. So say we're testing for a pathogen in a lot. So our small m number in our sampling plan is 0. And increasing the number of samples in this case really increases the likelihood of accepting unacceptable products. So if we look at a defect rate of 5% or greater than 5%, the number of samples needed for meaningful information is a major drawback. If we're willing to accept that our sampling plan fails 5% of the time, there is little probability the lot will be accepted when 60 samples are tested. And when 15 samples are tested, the defect will be about half of the time. So about half of the time, we're going to see our food defected. And so that's really great. If we're willing to accept 95% of the time our food will be safe and we collect, at 5%, we're pretty confident. But the problem is that when it comes to food safety, defect rates often tend to be a lot lower than 5%. So here we'll look at the 1% line. So we're talking about only 1% of the servings of your food are defective. And this is often the case when we talk about outbreaks. We're talking about using a defect rate of 1%. So if we're only collecting 15 samples, our lot will be accepted even though there's pathogen or whatever we're sampling for in the product 86% of the time. And if we're collecting 30 samples, 74% of the time when there's a problem, we won't find the problem. And even if we're collecting 60 samples of our food product and there's a 1% defect, 55% of the time we still won't be able to find that defect even when the food is being sampled. So with the number of servings that are consumed around the world, this is really why we can't rely only on sampling to detect a problem, and it's why we really need to talk about process control. And I missed skipping ahead to show all these different lines. Now, where and when should we test for food safety management? And you know, the reality of this is that testing costs money, time, and effort. And therefore, it's essential to decide what to test and when to test in a thoughtful manner. And so testing is really recommended when there's good evidence that there's a microbiological problem, either for safety or quality, and that you can have some control over it. And this may be associated with historical issues or a current situation that warrants investment. And there also needs to be good evidence that testing will actually help you control the problem. If the testing is not going to make a meaningful impact, then diverting resources into testing it doesn't make a lot of sense. And instead, putting those resources that you were going to spend on testing into other areas that will make a difference is really common sense. So basics, right? You guys know difference between validation and monitoring and verification. We're really going to focus for the next maybe 10 slides on verification activities. And so when we talk about verification activities, one of the different verification activities that exists is product sampling and testing. And this can be a lot of different things, but we're gonna really focus on talking about this for the next little bit. And so when we talk about product sampling and testing, periodic verification may be used, right, to look at those ingredients or the in-process materials that I talked about earlier on, or really some of our finished process. And really the goal is for you guys to understand and be able to figure out when it's important to look at those different areas. So one of the things that we can talk about is the difference between within lot testing and between lot testing. And within lot testing is used to establish the safety or quality of a specific lot of product. And this is such as the testing of ingredients or product at different points in the manufacturing chain. And really targeted testing within lots is important when we don't have a lot of knowledge about what's gone on with that lot. Now, conversely, between lot testing is based on a detailed knowledge of the product and the process. So between lot testing doesn't focus on a single lot, but rather it considers variations within a lot and variations between different lots of the same product being produced. And so between lot testing verifies that processes and practices are being performed as intended, and that's important for evaluating process control within a facility. And I'll step back just briefly to say that within ICMSF Book 8 that I introduced earlier on, there's a lot of recommendations for within lot testing to figure out more information about what might go on within individual lots. Now, this chart illustrates some hypothetical data that you can get from just different testing results. In this first case, we are testing for absence of a pathogen for a product that's used for a verification activity for process control. So in this one example, in lot 8, we were able to determine that there was a pathogen present through testing. Now, the problem is when we detect pathogens only within a lot, it's difficult to know whether the other lots produced may have a low level of contamination that was not detected. So another way that we can do this sampling is to do a quantitative testing using an indicator, and that's the data showed in the second graph that I just put up there. Now in this hypothetical example, the dotted line, I should say, the red line indicates the maximum acceptable level. And the data indicate that the lot 8, so this lot that tested positive in presence absence, also exceeded our sample exceeded our standard in terms of quantifiable testing, but then all of the other lots are within the acceptable range. No trends are indicated by that quantitative data. And so really we're talking about just needing to worry about what happened in that one specific lot. Now, one of the important things you should do if you are taking in-process testing data is to do trending of that data. And it's a really important tool for verification data. And some processes, like those with raw ingredients, may have substantial variation, right? Especially if you're bringing in ingredient products from all over the world. When using micro count data, the lower confidence interval is typically not considered important, but you do want to look at that upper 95% confidence interval. So in this case, you can see that we've exceeded our confidence interval in a couple of cases up here. And so what we want to do with that is look that we did see a trend upward, and we would want to have made some sort of either a process adjustment or reevaluate our suppliers if this is a raw ingredient towards watching that when we watch that trend going up. And there are a bunch of different types of trends that you can look at when you're looking at ingredient data. So we've seen this example I put up already where only one was out, but we can see in the second case that I put up here, we've got an increasing trend in our data that indicates some sort of a lack of control. And it might be something, in this case, this might indicate something like a sanitation issue, you know, or a problem again with an ingredient supplier change. Or we might see huge variability in our data. And that variability can be caused by a bunch of different things. Maybe it's seasonal variability, but you do need, when you see this kind of variability in your testing data, then you really need a fair amount of data to see what is normal and what is not normal. And then this final example talks about a situation where, you know, we had established baseline testing data, and then all of a sudden we saw this trend up, and our new test line or our new baseline data is well above the test. And so, you know, this should trigger questions within you in the data you're collecting. Did you change an ingredient used? Is there some new employee working? Has there been a process malfunction? Is it due to seasonal variability? Are we finding pathogens through other testing? You know, and so it really makes you want to think about your testing and what the data is you're getting. I'm going to skip this slide really quickly. So we talked a little bit about where and when to test, and I want to go into some more details about how to help you determine where and when to test. And I'm going to point to the ICMSF Book 8 for recommendations on this area. So as I mentioned earlier, within Book 8, there are a number of chapters at the end that go through specific examples for different food commodities. And so at the end of each one of those chapters per food commodity, there is a table present that talks about the relative importance for testing at different points, including end product testing. So where the point is, the relative importance is given as well, and then what useful testing might occur. And they often go through to even, especially in end product testing, but in different types of testing as well, tell you what microorganisms you should test for, and then what those criteria of the testing plan should be. So little n, the number of samples, C, the number of times you can be in that marginally acceptable range, small m, that lower limit for what's acceptable, and then big M, the upper limit for what's acceptable. And they talk about it in this, and this is the example for fresh cut vegetables, and it talks about it both in the cases of the indicator E. coli, and then more so also in the case of pathogenic microorganisms that might happen in an end product. Microbiological criteria define the acceptability of a product. So these are the numbers that are going to establish your big M and your little m. And they really, need to be some sort of a hard limit if they're not just presence absence. And it's often tricky to figure out what those numbers should be. So ICMSF does recommend a number of different sampling plans. And those sampling plans really talk about looking for a potential for contamination, such as detection of a pathogen in environmental samples or elevated counts of indicators. They also apply when production conditions and history are unknown, or for example, when you've got an unknown lot of incoming ingredients. And they typically represent a within lot testing approach. And when we talk about accepting food into our facilities, we talk a lot about lots. And depending on the ingredients, production, and processing methods, food lots may contain different microorganisms occurring at different levels. And to determine whether a lot is acceptable or not, the Commission really recommends using sampling plans. And these sampling plans' performance is proportional to the relative risk of consumers. And as we really recommend two different types of sampling plans, and I'll just go through them quickly. The sampling plans, again, there are 15 of them, and they are based on two different factors: the importance of the hazard, ranked on a category of 1 to 5, and food handling conditions, ranked on 3 different conditions. And those three different conditions are whether or not pathogens grow, survive, or die in a food product, or bacteria grow, survive, or die in the food product, and the amount of sampling increases as we go to higher risk products. So those 5 different categories of microorganisms include utility organisms that are spoilage, indicator organisms, something that's a moderate hazard, something that's a serious hazard, and something that's a very severe hazard. And again, we've got these 3 different terms, and I'm skipping over this really quickly, but if we look at these 15 different plans that are based out, again, likely change before consumption. Here we've got pathogens die in the product, or bacteria die in the product, they don't change in the product, and they increase in the product. And then the category, right, is these utility organisms, indicator organisms, moderate organisms, and then if they're serious or severe. For these ones, we recommend an enumeration technique. For these ones, we recommend a presence absence in an analytical unit of 25 grams. These top data here, there are 9 of them, and they are all 3-class plans. And these bottom numbers here, the recommendations are all those 2-class plans based on presence absence. And so again, tells you the sample number to collect, and in the case of these 3-class plans, how many samples can be within a moderate range. And again, these bottom numbers are analytical units where we're testing 25. And you can see our C is always 0 because there cannot be any of these pathogens in a product. So just an example of what this looks like. So something like an aerobic plate count, we might say we have a 3-class plan, we're collecting 5 samples, and 3 of those samples can be sort of in our intermediate range. Our little m is 1,000, so if it's got less than 1,000, the product is good. Our big M is 10,000, and so that 10,000 is bad, and so we can have 3 of our 5 samples between 1,000 and 10,000. So that would be this case here. And if you look at case 15, which is our sort of most severe case, where we've got a pathogen in a food product where it may increase, we've got a 2-class plan. We're taking a 25-gram sample. We want nothing detected in that 25-gram sample, and our N equals 60. And if you run the math, what that means is that we've got less than 1 CFU of E. coli O157H7 per 2,000 grams of the product. And so the book and this table and these 15 different sampling plans are really, really helpful as a way to help you determine how many samples you should be taking and what those sample sizes should be. And just an example here, so Salmonella is typically a case 10 organism. If it's in a food product where it won't grow, they say you select 5 samples. None of those 5 samples can exceed the microbiological limit, and the limit is less than 0 per 25. And that would be, say, something you would use on a refrigerated poultry product. So I'm going to skip through a bunch of these next slides because I'm way over the time. I spent a lot longer talking about things than I meant to. And I'll end on this. I've talked a lot about this book, Book 8. I want to let you know it's available here online through Springer. You can also find it on Amazon and at a number of used bookstores. You can purchase it electronically through Springer. And if you just are worried about your specific chapter, or a specific chapter related to a product that you are working with, those individual chapters can be purchased. But if you're going to purchase more than 4 or 5 chapters, you're better off just purchasing the whole book. These chapters are also available through some libraries, like the University of Florida. I used to say email Travis if you wanted a copy of one of the chapters of this book, but since so many of us are Travis right now in our signing in for this account, I won't tell you to contact Travis, but you can reach out to me or Travis, or again, it's available by Google. But I will tell you, microbial sampling is really, really complicated, and developing a good sampling plan is hard. And I don't know if I made it any easier for anyone today, but hopefully I have prompted you to ask some questions about your sampling plan and look into it more. And with that, I will take questions. I will also recommend to any of you, if you are trying to describe microorganisms to young children or young people in your life, there's a book called Do Not Lick This Book that I highly recommend. It's by Ian Benbarek and Julian Frost, and they are not sponsors of mine. I am just a big fan of this book for describing bacteria to young kids. And with that, I will gladly take any questions if there is time.
That was the perfect segue into one of the questions we have, which is, are there any resources to establish those acceptable, marginally acceptable, and unacceptable criteria? So it sounds like you were addressing that in the book previously too.
Yeah, and I will say, like I said, I think, way back, I showed this table that is present for each of the chapters in this book. And in this table, ICMSF does make recommendations for what those limits should be. In this case, they've only done it for end product testing, but in different commodities, they'll show it in different cases. And so in the slides that I didn't go through because I ran out of time, I will show one example here. And what those criteria are going to be might be different depending on the different uses of the product. So in this case, we're talking about cocoa powder as an example. And so if it's used in chocolate that doesn't have a heat treatment, or if it's used to just dust on, cocoa powder used to dust on top of a baked good, it might have a lot higher, more stringent factors than if it's going to be used in an ice cream mix that goes through pasteurization. So there are recommendations in the book, but those recommendations really do vary based on the use of the product as it's moving forward.
That is really helpful. I think you answered everything. I don't have any other questions at this time.
Oh, amazing. Well, thanks you guys all for joining me, and I will turn it back over to you.
Thank you very much for that very helpful talk. We very much appreciate you coming and doing the talk for us, and we also appreciate all of our attendees for attending this webinar. You'll be able to look at our new and improved website to see the upcoming webinars that we have. Our next one will be 2 Wednesdays from now on August the 5th, where we have Dale Grinstead discussing listeria in the retail environment. After that, we have another on the 19th of August, and September 2nd and September the 16th. So we hope to, and then from there, we hope to organize some more speakers to provide more webinars for us. If you have any ideas or speaker recommendations, please feel free to let us know about those. We're always willing to hear ideas from our membership. If you check out our new website, you'll see that we have these webinars, webinar links for registration posted there, as well as a method for you to submit speaker ideas for upcoming webinars. And with that, thanks everyone again for attending today, and enjoy the rest of your day.